Section 1.1 is on page 2, talks about angles and their measures. So here, an angle is formed by two rays. In case you're not familiar with this, well, actually you should be familiar with this because you could take in geometry for this. Two rays sharing a common vertex. We call one ray the initial side and the other ray the terminal side. So a couple of ways of doing this. If I take one ray and another ray. So an angle is formed by two rays sharing a common vertex. This right here is the vertex, in case you've forgotten. I could be talking about the angle being right there, right? No need for direction. Or I could be talking about the angle being right there. There's no telling. I could say, look, this is the initial side, and this is the terminal side. Or I could say, wait a minute, that's not true. This is the initial side, and this is the terminal side. Meaning this is where I begin, this is where I end, depending on which angle I'm talking about. So this definition is not really specific. When I say sketch an angle of 30 degrees, well, you could say, here it is. You could say, this is 30 degrees. You're right. Somebody else in this class might sketch a graph and say, oh, look, oops. Look, that's my 30 degrees. And they're correct as well. So, for us to be talking about the same measure and the same shape, we make an angle standard. What's a standard angle? An angle is said to be in standard position, and all throughout this course we're going to be using standard angles. An angle is said to be in standard position if its vertex is at the origin. If I glance at the traditional x and y, and I set the center to be at the origin, and the initial side coincide with the positive x-axis. What does that mean? That means I would always start on the positive x-axis. Not only that, if I rotate in a, I always have to look at my watch, in a counterclockwise manner we say that's positive, and a clockwise manner we're going to say that's negative. And from this we are aware of how this plays. Now remember, the actual grid looks just like that. The positive x-axis, nothing more. That's really how it looks like. So you start on the positive x-axis. The only reason I'm putting the grid on, just for reference, knowing that, you know what, if I rotate one full revolution, I know that's 360 degrees. Half of that is 180 degrees. Half of 180 is 90 degrees, and this is 207 degrees. Just for reference. And if I look at the first problem, draw each angle. From now on, all throughout this book, the book starts on page 11. On page 11, they say, draw each angle. We're talking about standard. So every time I want to sketch a graph, I start on the positive x-axis, and I rotate to 60. Now let me use a color that's hard to see. So this yellow part or shaded part is not there. I'm leaving that for reference. If this is 90 degrees, half of it, this is half of it, that's 45 degrees. 60 should be a bit more than that. I'm not going to get a protractor and measure, but anywhere you line up above halfway, me and you are very happy, and you could say that's 60 degrees and we're fine. So you start on the positive x-axis being 0, and you rotate. If it's positive, you rotate in a counterclockwise manner. If it's negative, clockwise. I look at problem number 14 on page 11 in our book. So this is section 1.1. Negative 120. Well, I know this is negative 90. So it has to be more than that. If you add 90 to that, that's 30 more. So halfway is about right there. It has to be a bit short of that. So anywhere short of the 45 degrees, which cuts that in half, is acceptable. And you could say this is negative 120 degrees. Again, you start on the positive x-axis and there it is. 540 degrees, well, that's a bit too big. If I make one full oscillation, that's 360. If I take away 360 degrees, that's 0. That's 8. That's 180 degrees. So I need to rotate 180 more. I'll end up pointing in that direction. This is 540 degrees. So whether I rotate 540 degrees or 180 degrees, I'm pointing in the same direction. Now, one full revolution around the circle is 360 degrees, but there's also another measure for that. We say that's 2 pi radians. 2 pi radians is equal to 360 degrees. If I divide by 2 both sides, pi is 180 degrees. I'm going to use that as a scale anytime I want to convert back and forth. And if I wanted to know what 1 radian equal, if I divide by pi both sides, divide pi by pi, that's 1, divide 180 by pi, if I take 180 and divide that by pi, I'll get roughly 57.3 degrees. 1 radian is roughly 57 degrees. But this is really what I'm going to use all throughout the course. So in the beginning, we will learn about radians much. We're going to learn a lot more about radians. For now, if you know where 4 pi over 3 is, you could just graph it if you've seen this before. If not, to convert from radians to degrees, I want radians at the bottom, pi is the radians. And the degrees, you always must put that 0 power. Those cancel out. 3 divides 18 6 times, and 4 times 60 is 240 degrees. So if I start at 0, this is 90. This is 180, so I have to rotate past that. From 180 to 240, that's 60 more. So I have to go past kind of like the midline. I went a bit too far. So if I go past, you know what? And if I go outwards a bit, you could see it better. There. Anywhere past the mid, that is 240 degrees. So I'm pointing in that direction in quadrant 3. Negative 2 pi over 3. If you don't know where that is, you could sketch it. If not, you could rotate it to 100 degrees. Pi's cancel out. It's negative. 3 divides 18 9 times. I'm sorry, 6 times. Horrible with math. 2 times 60, 120 degrees, and we just did that. So here, I suggest, even though it's 240 degrees, I suggest you label that 4 pi over 3. For now, you're not going to like radians if you've seen this for the first time. Once we learn about radians, you're going to like that a lot more than degrees. Negative 120 degrees, so this is negative 90. Negative 120 degrees is about right there. Again, I'm not going to get a protractor to figure this out. And it would be best to label this as negative 2 pi over 3, the original. Now, convert each angle in degrees to radians. Alright, so take 120 degrees, and if I multiply that, again, if I want the answer in radians, I want radians at the top. Whatever I want to eliminate, I want that in the denominator. The zeros cancel out. Divided by 6, that's a 2. Divided by 6, that's a 3. So 120 degrees is the equivalent of 2 pi over 3. 330 degrees. If I multiply, I want it in radians. Radians at the top, degrees on the bottom. Those cancel out. Thinking this is 3. Divided by 3, that's 11. Divided by 3, that's a 6. 270 degrees. If I multiply by pi over 180, the degrees cancel out, the zeros cancel out, divided by 9, that's a 3, divided by 9, that's a 2, that's the equivalent of 3 pi over 2. Negative 225 degrees, if I multiply by pi over 180, that is negative, the degrees cancel out. If I divide by 5, 5 divides 20 4 times, 2 left over, 5 divides 25 5 times, 5 divides 18 3 times, 3 left, 3 divides 36 times. If I divide by 9, that's a 5, and if I divide by 9, that's a 4. There. The next section, the next part of the homework says, go backwards. Given radians go to degrees, well, hey, multiply degrees at the top. Whatever you want the answer to be in, you put at the top, radius in the bottom. The pi's cancel out. 6 divides 18 3 times, so 5 times 30 is 150 degrees. If I do the same right there, multiply by 180 degrees over pi, pi's cancel out, divided by, I divide by 12, but I don't know if you can see that. Let's divide by 6, that's a 2, divide by 6, that's 30, divide by 2, that's 15, and that is 25, 75 degrees. 5 pi over 12 is the equivalent of 75 degrees. If I look at 50, multiply by 180 over pi, pi's cancel out. The answer is negative. 3 divides 180 or 1860 times. 2 times 60 is 120 degrees. And if I multiply by 180 degrees over pi, well, those cancel out. That's negative 180 degrees. So, sort of, kind of straightforward. If you look at a circle, given a circle with a radius r, if I take the radius, remember the radius is the distance from the center to the circumference. If this is r, and this is r, central angle theta is right there. That's an angle that has its vertex on the center of the circle. If you take this length, we call that s. If we take the walking distance on the circle and we put it on a flat surface, that is the radius times theta. And if we take this area, it's called area of a sector. That is 1/2 r squared theta, provided theta is in radians. If theta is in degrees, that wouldn't work. So if I want to take this distance s, instead of being a circle, put it on a flat surface, that's the formula for it. And if I want to find that area, there it is. Number 88 says, find the length s. Well, how do you find s? S equal r times theta. This s is, the radius is 4, and theta is pi over 6. S would be 2 pi over 3. And since it's like perimeter but on a circle, that takes meters. If I want to find the area, I'll say that's 1/2 r squared theta. Area will be 1/2. R is 4 squared times theta, which is pi over 6. A will equal, this is 16. 2 divides 16 8 times. And if I divide by 2 and divide by 2, that is 4 pi over 3. What are the units for area? Whatever this is, squared. What if they try to trick us? Well, first, before I begin, I must take theta and convert it to radians. Otherwise, it doesn't work. So the angle is 5 pi over 18. I know that doesn't look pleasant, but there's nothing you can do about that. If I take the walking distance, s, S will be R times theta. S will be R is 9 times theta, 5 pi over 18 centimeters. S would be divided by 2, that is 5 pi over 2 centimeters. And the reason I put centimeters there, I don't mind you leaving the answer like this on a test. And if I look for area, area is 1/2 R squared times theta. Area will equal 1/2 times 81 times 5 pi over 18. If I divide by 9, that would be 45 pi over 4, and the units would be centimeters squared. And that's pretty much it. I was tempted to stop this video here, but we're almost done. Let me check. Yeah, I'm gonna finish this video. It takes about a couple of more minutes. It's not enough time to do it in a different video. Well, let S denote the arc length. And let theta be the subtended angle. Find the missing. Well, S, R, and theta, we know that S equal R times theta. What's the catch? Theta must be in radians, and it is. So find S. Well, S equal, what's the radius? 6 feet times 2, that would be 12. The units for S is always feet, and the units for area would have been square feet if that was the case. Number 76, they give us S, and well, S equal R times theta. They say, hey, theta is 8, S is 8 meters. So if I put 8 right there, radius is 6 times theta. What would theta equal? Theta would be 8 over 6, which is 4 over 3. And if you don't write anything, you're saying it's radians. If it's degrees, you must give it sort of like that 0 power. But if it's not, then you really don't have to worry about it. And number 78, S equal R times theta, but here they're trying to trick us, but we know better. Theta is 120 degrees times pi over 180, because I want it in radians. Those cancel out, divided by 6, divided by 6. Theta is 2 pi over 3. So that's simple. Now that I know that in radians, then I could say, well, S equal R, and instead of saying 120, it's 2 pi over 3, and that would be 2 pi meters. And they do the same, but they do it for area. Same deal here. Let A denote the area of a sector. Well, area equal 1/2 R squared theta. In this case, they're looking for area. Okay, 1/2. Radius is 6, and that's already in radians. And the units for that are going to be squared feet. So again, on a test, I don't mind you giving me the answer like that. Those twos cancel out. The answer in the back of the book for the homework, you should match. It's 36 square feet. And here I noticed that they give us, they want R, they give us A and theta. A equal 1/2 R squared theta. The catch, you want theta to be in radians, and it is. So A is 6, 1/2, R is what you're looking for, theta is 1/4. So if you clear the fractions, 4 times 2 is 8. 48 equals R squared. And R will equal the square root of 48. And the units for that would be centimeters, or R will equal, that will be, what is it? 6 times 8. So that is 2 times 3, 4 times, so that is 16 times 3. So that is 4 radical 3 centimeters. Again, anything I box, you could leave your answer like that on the test. And the homework is right there.